Okay, so this is problem number 3 from your review worksheet, which is the banked curve. And in this first part, there is no friction. So I'm going to draw a force body diagram here as mg. That should be straight down. I know it's kind of angled. And the normal force. And that's it. There's no other forces on this diagram. So as it goes around the bank curve, we do know that there should be an acceleration toward the center of the curve. That's what centripetal acceleration does. So if we look at this diagram and we're trying to find that leftward force that points in the direction of acceleration, then we would notice that the normal force does have a component that points toward the center. So the way I usually draw my force body diagrams, because I am trying to find where that angle is I take the normal x and y axis, and as I rotate my y component in the direction of n, I can see that this is where my 15-degree angle is, which would also be in this direction as well. So what I can see is that the acceleration centripetal, or let's say the centripetal force rather, is equal to the normal sine of theta, and that's mv squared over r. So from this point, you should be able to solve it pretty easily. We do need the normal force. So this right here is the y component. I need the x component to find the normal. So normal cosine theta has to equal my gravity, because that's pointing straight down. And that means that the normal is equal to mg cosine theta. I plug that into this normal and I get mg sine theta over cosine theta, which is tan theta. You're going to notice that a lot of you might think, well, I don't have mass. How can I solve for this? For circular motion, mass always cancels out for your centripetal force. So in the end, we get a velocity is equal to the square root of rg tan theta. And if you plug in the values, you should get 16.4 meters per second. Okay, so part B, we now have a track that has friction. So I'm just going to redraw my force body diagram with the same forces as the previous one, but now I have to add friction in there. One thing I want you to note is that this car is traveling around a bank curve, so it's coming out at us, and if there was no friction and it was moving really fast, that car would fly out of that banked curve to the right. And so it's friction that keeps it in motion around the bank curve. So unlike a scenario where you have that car just sitting on that banked road, if it was just sitting there, it would slide down, and so friction would point up and to the right. But when it's moving, inertia wants to pull it out, which means friction opposes that outward motion, and friction actually points in. So these are kind of little tricky concepts that often cause errors in these types of problems. Okay, so I've got my 3 forces, and I know acceleration is pointing to the left. So this is my positive direction, and I'm going to call upward the positive y direction. And I need to figure out how to break up my components so that I have them in my x and y axis. So friction is going to go to the left and down. This will be my theta. For the normal force, it's going to go up and left. So this will be my theta. And all we have to do is break it up into x and y components. So part C is hard because of all the variables that can make it really messy. But if you just do it by breaking it down into x components and y components, it's simple. It's really just the algebra that's difficult. Okay, So x components left is positive, so I've got a frictional force, which is F cosine theta. I'm going to call that the positive direction, and the normal direction is normal sine theta. I'll call that positive, equals our centripetal force. For the y component, I've got a normal component that's pointing upward, and cosine theta minus friction sine theta is equal to, or sorry, minus mg is equal to 0. The goal here is to solve for coefficient of friction. So what I'm going to do is I'm going to rewrite my friction as force times normal for both sides. And this is mu is force minus force times normal sine theta. Okay, my next step is I want to isolate mu. Unfortunately, we have mu in both equations, and we also have normal in both equations. So anytime you see something like that, you have to solve for the variable in one equation and plug it into the other. I am going to solve for normal here, which means I'm factoring out this, and I get cosine theta minus mu sine theta. I'm going to add the mg to the other side because I know that I'm going to need to isolate normal anyway. So I get cosine theta minus mu sine theta in the denominator. This is what I'm going to plug in to this equation. So it's going to look ugly, very, very messy, but that's okay. We are going to do it slow and step by step. So mu times the normal force, that's mg. I'm going to multiply this cosine theta and then the denominator. And then I'm going to add this, and let me just make sure I'm doing the signs correctly because I always mess up my signs. mg, I'm going to add this sign in there, over cosine theta minus mu sine theta is equal to mv squared over r. What's nice about this is that we've got common denominators. This and this can be factored out and multiplied to both sides. So I now get something that is not so messy with a bunch of fractions in it. And I'm going to do this because, again, I don't like fractions, but I'm going to multiply both sides by r to get rid of this denominator. So mu r mg cosine theta plus r mg sine theta is equal to mv squared cosine theta minus mv squared mu sine theta. So I distributed the mv squared and I multiplied everything by r. Okay, now how do I get my mu on one side? How can I isolate that? I have to bring this whole section over to the left, this section to the right, and I also have noticed that I've got m's all over for every single expression, so I can factor the m out and cancel it out. And I am going to, again, this mu is gonna, or this expression is gonna add over, and I'm gonna factor out the mu all in one step. So hopefully this algebra, I'm doing multiple steps in one, doesn't confuse you. And then I'm gonna take this expression, bring it over to the other side. So I've got v squared cosine theta minus rg sine theta on the right side. And I'm just hoping I didn't mess up any signs here. Okay, now I just do a simple division. V squared cosine theta minus rg sine theta all over RG cosine theta plus V squared sine theta. Just checking my work here. And then I'm not going to do all of the work to plug in the values. You guys can plug in all the values, but I ended up with something like 0.30 for my mu. I think the answer key says 0.32, probably due to some rounding errors, or maybe they use 9.8, but if you get this, then you are correct.